String theory is a fashion, quantum physics is faith, and cosmic inflation is fantasy. Do you know who is the one who said this? This is none other than the legendary physicist and Nobel laureate Roger Penrose. String theory is considered one of the fundamental theories in physics, but Sir Roger Penrose completely rejects this theory and believes that it is totally wrong. But that's not all. He goes further and claims that quantum physics and cosmic inflation are also wrong. So what is string theory? Why does Roger Penrose say that string theory is wrong? And if it is wrong, what alternative theory does Roger Penrose propose to explain the nature of reality?
If you could have a theory which had predictions, and these predictions could be seen to be right or wrong, that's what I understand about physics. But string theory seems to me driven largely by certain ideas which have importance in mathematics, but sort of irrelevant to the physics, really.
Let's start with what string theory is.
What I do for a living is string theory. That's my day job. And you see, string theory is a multiverse theory. So people say, first of all, what is string theory? String theory simply says that all the particles we see in nature, the electron, the proton, the quarks, what have you, are nothing but vibrations on a musical string, on a tiny, tiny little string. You know, J. Robert Oppenheimer, the creator of the atomic bomb, was so frustrated in the 1950s with all these subatomic particles being created in our atom smashers that he announced one day that the Nobel Prize in physics should go to the physicist who does not discover a new particle that year. Well, today we think they're nothing but musical notes on these tiny little vibrating strings. So what is physics? Physics is the harmonies you can write on vibrating strings. What is chemistry? Chemistry is the melodies you can play on these strings. What is the universe? The universe is a symphony of strings.
String theory is undeniably one of the most favored theories in physics that is widely overused in pop culture today. Numerous well-known scientific communicators nowadays have definitely talked about this theory at some point, like Neil deGrasse Tyson, Bill Nye, and the two Brians, Brian Cox and Brian Greene, all of whom are names that are admired in the scientific community. And we can't blame them, since this is truly one of the most contentious and daring theories of physics at the current date. According to Dr. MICHIO KAKU, a well-known popularizer of science and highly esteemed theoretical physicist, string theory can address a myriad of questions about our very own universe. What events occurred at the edge of time and space precisely before the Big Bang? What precisely can we anticipate inside a black hole? And even the possibility of instant travel in space up to parallel universes through what we call wormholes.
It was in all the papers that a great scientist had just died, and they put a picture of his desk on the front page. That's it, just a simple picture of the front page of the newspapers of his desk. That desk had a book on it, which was opened, and the caption said, more or less, "This is the unfinished manuscript from the greatest scientists of our time." So I said to myself, well, why couldn't he finish it? So to me, this was a murder mystery. This was greater than any adventure story. I had to know why the greatest scientists of our time couldn't finish something. And then over the years, I found out the guy had a name, Albert Einstein, and that book was the theory of everything. It was unfinished. Well, today I can read that book. I can see all the dead ends and false starts that he made. And I began to realize that he lost his way because he didn't have a physical picture to guide him on the third try. On the first try, he talked about clocks and lightning bolts and meter sticks, and that gave us special relativity, which gave us the atomic bomb. The second great picture was gravity, with balls rolling on curved surfaces, and that gave us the Big Bang, creation of the universe, black holes. On the third try, he missed it. He had no picture at all to guide him. Well, today we think that picture is string theory.
I think you can't fathom how much of the current trends of sci-fi have proliferated because of these ideas existing. Let's take a profound dive into what exactly this theory is, shall we? Or at least try to achieve that, since even the scientists who study this theory are also still struggling to fully comprehend every aspect of it. The story of string theory commenced when physicists desired the most simplified explanation for everything in the universe. Scientists always have this thing of wanting to compress explanations into something as tidy and as simple as possible. Specifically, they were aiming to find a single line of the equation that can be used to describe every phenomenon in the universe, from how a fly moves in the sky and how planetary motion comes about, to how electricity functions. It would undoubtedly be something astonishing if only we could describe all of this in one line of math, doesn't it? Back in the early days of modern physics, there were 5 fundamental forces of nature known: electricity, caused by the motion of electrons; magnetism, which describes an inherent physical phenomenon of objects; the weak nuclear force responsible for nuclear decay; the strong nuclear force, or the force holding together the nucleons in an atom, keeping them from breaking apart due to the repulsive force of the electrostatic force. The earliest success at unifying these forces was done by James Clerk Maxwell when he laid down the equations that defined the interrelationship between electricity and magnetism. According to his study, an electrical current can induce magnetism and vice versa. The resulting theory was called electromagnetism. Fast forward to the early 20th century, and the quest takes us to 2 of the most well-known theories in physics nowadays: the theory of general relativity, which best describes the extremely large and massive, and quantum mechanics, which describes the extremely light and small, both of which had some, if not most, involvement by physics superstar Albert Einstein. By the way, quantum mechanics reveals that every particle has a dual nature. Everything has both a wave-like and a particle-like property. However, this is not entirely pretty, as in this approach, the best we can come up with are probability expressions of particles. But does it accomplish the task of describing subatomic particles and how they interact with the highest accuracy? Despite this incapacity, before you label this theory as bananas, it's important to know that it is not entirely the scientist's fault. What quantum mechanics also reveals is that when we try to observe particles on the quantum scale, this observation has a consequential effect. You might be thinking, how did we come to that? I thought we were doing so well. Well, as it begins, we're limited by our means of observation. For us to actually observe something, we have to experience it. Usually, this experience entails seeing things and recording what we see. A pretty easy task, right? Well, at some point, it stops being as simple as that. Take note that to be able to see stuff, we need to have a light wave hit an object and then have the light wave bounce at our eyes, at which point our brain interprets the information. When we are talking about subatomic particles, these objects can get so small that effectively visible light won't be able to bounce on them, so we can't effectively make an observation. So let's use light with a shorter wavelength, right? Well, not entirely. Using this configuration results in an extremely high amount of energy that would affect the position of the particle. In more compact terminology, this is known as the Heisenberg uncertainty principle, which states that we can never accurately have information about both how fast an object is going and where exactly it is located at a certain time. This is what we stated earlier in the quantum realm. The observer also affects what he observes. Are you still keeping up? I know this is getting extremely tedious, but I promise you this is going to get more interesting, so please bear with me. Now let's discuss what's on the other end of the spectrum: Einstein's general relativity. Back in the days of classical mechanics, Newton described gravity as some sort of non-contact force, essentially, force affecting objects without actually being in contact, or as he put it, action at a distance. This was extremely controversial since the current understanding at that time was that for energy to be transferred to objects, it had to directly come into contact. But the math works, and upon observation, this also works, so it held up as a theory after 200 years. This theory was all good, until then came Albert Einstein, who changed everything from the ground up and claimed a different take on it. In Einstein's revision of the gravitational theory, which he labeled as general relativity, he completely revised the claim that gravity is a non-contact force and addressed the problem from a different perspective. In his theory, he stated that we're looking at space all wrong. The problem is that we're assuming time to be the most constant quantity in the universe, which, as he described in quantum mechanics, is not. Instead of just having space, he claimed that space and time are a single membrane to which everything is bound. So if that's the case, what exactly is gravity? To help you imagine, say for instance that you stretch out the fabric and then you put something heavy in the middle, like a bowling ball. If you add marbles to it, which are way less massive, then you expect the marbles to swirl toward the center. Relating this to gravity, the mass of heavy objects in space-time causes them to effectively become distorted. This is what we experience as gravity. If we take our solar system to our analogy, the sun is the bowling ball, and the planets are the marbles spiraling about. This solves the non-contact conflict, and physics is bound again by its original laws of order. Now we have two outstanding theories that define their respective realms with great precision. For the cosmological, we have general relativity. For the subatomic, we have quantum mechanics. This is where the challenge begins. Quantum mechanics works with probabilities, while general relativity deals with definite stuff. If the goal was to unify the forces, this is certainly not helping. So how did physics tackle this problem? One idea they had was that maybe if we could know what the most fundamental component of nature is, we could find out how to unite these forces. So in the 1900s, this is what they did. They collided protons together and found out that they are indeed composed of much smaller particles, which they called quarks. Some quarks are responsible for the characteristics of matter, such as mass, charge, and angular momentum, while others are responsible for the forces. This theory unified the electromagnetic and weak force into the electroweak theory. Apparently, forces are merely, somehow, a particle exchange. To oversimplify it, this is more popularly known as the quantum field theory, eventually giving rise to the Standard Model. If this is the case, then particle exchange still needs a place to operate. If it needs a place to operate that interprets to space-time, and as described by Einstein, if we were to assume space-time to be non-dynamic, that is to say, you can't change its features, then we're going to be stuck in a loop. We won't be able to unite the two theories. One testament to how important this unification is what it will tell us about the beginning of the universe. General relativity is great at describing the extremely large and massive, while quantum mechanics the extremely small and lightweight. At the temporal edge, for lack of a better term analogy, at the beginning of the universe, everything was so dense, that is to say, extremely small but extremely massive. Literally, everything in this universe was at one single point in space. Talk about a crowded space in cosmology. Astronomers take a stab at this problem by studying black holes, since these celestial objects are extremely massive and small. It's not exactly like the Big Bang, but this is as close as we can get to it. And this is generally how we identify objects. We study something that has similar attributes and relate the information we get. However, I bet you can guess that that's not everything in the story. Now enter Theodore Kaluza, who dared to think in a similar and daring way as Einstein did. He thought, if we can describe gravitational force as a distortion of space-time, can't we think of the same for electromagnetism and other forces? Maybe they're also distortions of components much more fundamental than quarks. Lo and behold, a working theory was made. Upon further investigation, the more fundamental components of the universe apparently behave in a similar manner, precisely as curves and bumps in a field of membrane, similar to, you've guessed it, strings. This is where string theory rose to popularity. A more concise description of string theory is that the forces, the characteristics of objects such as mass, charge, spin, and energy, are all manifestations of vibrations of tiny strings of energy. To put it into perspective, it's similar to how changing the tension on a guitar string, for instance, produces a different note, and a combination of notes produces a different chord. However, as astounding as this sounds, there are mysterious consequences for string theory to be an accurate description of the fundamental forces of nature. It has to have dimensions that are more than what we can currently observe. In fact, in its latest variation, the M theory, the strings have to have 11 dimensions in which they can freely vary, and vibrations in these dimensions manifest as the forces or the characteristics of matter. Now don't think of these dimensions as what pop culture perceives them to be like, dimensions as in traveling to a completely different universe that also uses dimensions but in a different context. I have to stress that this is not going to get you overly excited and think of an actual different universal dimension that we don't know of. Although, in the deeper sense, it actually is the case. but let's move on. But okay, in the context that we are in, what are these dimensions? How do we know they exist? Well, the simplest way to imagine these dimensions is by looking at a power cable hanging on an electrical post. If we're far away, we interpret these cables as one line or one dimension. However, as we move closer, we'll see that the cable is actually cylindrical, with 3 more dimensions of length, thickness, and height. Is that all crazy for you yet? At now, string theory remains purely theoretical and mathematical in nature. In the past, the prevailing dogma in physics was to conduct experimentation first before developing theories. However, in the modern age, the approach has shifted towards establishing the theoretical foundation before performing experiments. This leads us to a crucial question. While string theory is mathematically consistent and theoretically sound, how can we actually test it? This presents a significant challenge in the field of string theory.
You know, Pythagoras was a rival of Democritus. Democritus talked about atoms 2,000 years ago. And Pythagoras said, no. Music is the language of the universe. So he looked at a lyre string and said, look at the vibrations. Each vibration corresponds to a musical note. The universe is music. The universe is created by vibrating things. Each vibration corresponds to a note. He went to a blacksmith where there were long bars of metal, and they were clanging these bars of metal. He realized that the longer the metal, the lower the note. There's a relationship between the length of the object, its strength, and the note. And then he looked at a lyre string, and he said the longer the lyre string, the lower the note. And then he said, this is the universe. What explains the diversity? What paradigm is rich enough to explain the diversity of the entire universe? Atoms, but what makes atoms different? And then he said, it's music. But then they never went anywhere, because of course the atomic theory wasn't created for another 2,000 years. But finally, with the atomic theory, we now have subatomic particles. But why do we have so many subatomic particles? They're nothing but musical notes on a tiny, tiny little vibrating string. So this is the electron, vibrates this way. This is a quark. This is a neutrino. So why do we have so many particles in the particle zoo? They're nothing but vibrations on a tiny string.
In today's scientific landscape, there are various approaches that scientists have devised to explore the existence of strings and extra dimensions. In a TED Talk by Brian Greene, a respected physicist in the field, one proposed method to test the existence of extra dimensions is by colliding particles in the Large Hadron Collider, or the LHC. But how would this work? When 2 particles collide, the resulting debris scatters in all directions and the energy changes can be measured using conservation laws. It's expected that the difference in energies before and after the collision should be the same. However, if for some peculiar reason they don't match, it could indicate the presence of the extra dimensions we're searching for. As intriguing as this sounds, up to this day, no test has been devised to definitively prove the existence of strings. The conditions required to observe strings directly are currently beyond the capabilities of our technology. Nevertheless, while it is not currently falsifiable, the mathematical consistency of string theory provides hope for future breakthroughs. Now let's discuss why Sir Roger Penrose says that string theory might be wrong. Roger Penrose has been a vocal critic of string theory, primarily due to its lack of empirical evidence and issues with falsifiability. In contrast to successful theories like general relativity and quantum mechanics, which have substantial experimental support, string theory remains largely untested. One of Penrose's main contentions is that string theory's complex mathematics might indicate a disconnection from the real world, potentially overlooking more elegant and straightforward explanations for physical phenomena. He has a preference for geometric approaches that offer deeper insights into the nature of the universe. Another crucial point of criticism raised by Penrose is a lack of falsifiability in string theory. For a theory to be considered scientifically valid, it must be open to the possibility of being proven wrong through observation or experimentation. However, string theory's proposals often involve extra dimensions and features that are currently beyond our technological capabilities to verify, making it difficult to subject the theory to empirical tests. Furthermore, Penrose has expressed concerns about the anthropic principle's influence on string theory. This principle posits that the observed values of physical constants must allow for the emergence of life. While some versions of string theory rely on the anthropic principle to explain certain fundamental constants, Penrose believes it might be a way to avoid seeking deeper and more fundamental explanations for these values. It's crucial to note that while Roger Penrose's criticisms have sparked debates within the physics community, they're not universally endorsed. String theory continues to be an active area of research, with many proponents who believe it holds promise in unifying quantum mechanics and general relativity. Despite the absence of experimental evidence currently, some researchers remain optimistic that future advancements in technology might render string theory testable. Now, as we've discussed at the start of the video, Sir Roger Penrose not only rejects string theory, but also has objections to quantum physics and cosmic inflation. Roger Penrose, in fact, has been critical of certain aspects of modern physics, particularly quantum physics and the theory of cosmic inflation. He argues that these theories go beyond what can be empirically observed and tested, moving into the realm of faith and fantasy. Penrose's skepticism about quantum physics stems from its inherent probabilistic nature. In traditional classical physics, events are determined with precision based on initial conditions, leading to definite outcomes. However, quantum mechanics introduces uncertainty at a fundamental level, suggesting that certain properties of particles, like their position and momentum, cannot be simultaneously known with certainty. Instead, they're described by probability distributions. While quantum mechanics has been incredibly successful in explaining many phenomena and making accurate predictions, Penrose believes that its reliance on probabilities and the lack of a deterministic explanation for the collapse of the wave function raise deep philosophical questions. He finds it unsatisfactory that we cannot determine the precise state of a particle until we observe it, and even then, the outcome is probabilistic. Penrose argues that this introduces an element of faith in accepting this interpretation of reality, as it cannot be directly measured or fully understood. Regarding cosmic inflation, Penrose is critical of the inflationary theory's speculative nature. Cosmic inflation proposes that the early universe underwent an exponential expansion, explaining various observed features of the cosmos, such as its overall homogeneity and isotropy. While the inflationary theory has gained wide acceptance due to its ability to account for certain cosmological observations, it also introduces several free parameters and relies on hypothetical scalar fields. Penrose contends that this inflationary hypothesis lacks substantial empirical evidence, and that some of the parameters in the theory can be fine-tuned to fit the data, leading to a range of possible scenarios. He views this as a form of fantasy, where physicists create intricate models that are not grounded in direct observation. Penrose advocates for more modest theories that are firmly supported by empirical data, and he remains skeptical of concepts that are difficult to falsify or test. But what are your thoughts on string theory? Do you consider it to be accurate? Should our scientists dedicate their efforts to proving this theory, or should they explore alternative theories? Do you think Roger Penrose is right? Please share your thoughts in the comment section below. And thanks for watching.